about enumeration in more depth. Uh, So, diving deep into enumeration, so let us get started. So, after a system restarts or power up, the configurations software scans the PCI Express fabric to discover the topology of the device is connected to the system. So this process is called enumeration. So now we will look after how it happened step by step. So at the start, the only known device in the system is host or PCI bridge. So what is the host and PCI bridge? You can see here, this is the host and PCI host, or you can say the PCI bridge. So what do we mean by host or PCI bridge? So the host to PCI bridge is like the main connection between the computer processor and the PCI devices. It is responsible for making sure that the processor communicate properly with PCI devices. So it acts like a translator between the two. So let us now move. So at the start, the only known system in the known device in the system is host or PCI device, which serves as the entry point for configuration and connects the processor and the PCIe fabric. The bridge assigns bus 0 to its downstream side, as known as secondary bus. So as you can see here, this is the image. It have assigned bus 0 here. So the rest of the topology including the device says on the other bus is yet to be discovered. So first thing happens is the processor and the root complex know that the bus 0 exists. So first thing is that the root complex uh, ge- gets to know that the bus 0 exists and the other buses and the devices are marked as unknown and are yet to be identified by the configuration software. So, scanning the PCIe fabric. So, enumeration involves the configuration software searching for devices on each bus by sending configuration read requests to each potential bus, device, and function combination. So, here's how this process is carried out: reading the vendor ID register. So the software attempts to read the vendor ID from each device configuration space. The vendor ID is a unique 16-bit value assigned by the PCI SIG to each manufacturer. It is like hard coded. It is hard coded into device configuration space. So by reading the vendor ID register for all possible bus, device, and function numbers, the software determines whether a device is present or not. So next is that during enumeration, the software might attempt to access a bus device function combination where no device is present. So in this case, the PCI fabric handles the situation by returning a completion with unsupported request status. So the upstream PCI bridge, which is above the target, generates this completion, and the root complex translates the result to all triple FH. So this is triple FH, that 4 like FFFH. So it returns which is a reserved value indicating the absence of a device. So the software interprets a vendor ID of FFFH as the device not being present So this prevents the system from falsely reporting errors. So now error handling during enumeration. So although a master abort error or a UR response could be seen as an error during a normal runtime, it is expected during enumeration and not treated as a critical issue. So the system uses a special unsupported request status bit to note these conditions without halting the enumeration process. So this is important to prevent unnecessary error handling during this stage, as the system might not yet have all error handling capabilities active. So there are cases when device may not is not ready to respond. So what happens in this case? So after reset, PCI devices require some time to initialize before they can respond to configuration access. So if the data rate is 5 giga transfer per second or less, the software must wait 100 millisecond 100 ms before sending a configuration request. So for higher speeds, example Gen 3, the wait time extend beyond 100 ms due to the time required for link training and equalization. Then configuration request retry status. So when a device is temporarily unable to respond to the configuration access, it returns a CRS status. So the status signals that the device is not yet ready, will be sh- but will but it will be ready shortly. So the root complex handles CRS differently depending on the system settings. So during enumeration, the root complex may return a vendor ID of 000001H, indicating a lengthy delay, which tells the configuration software to skip the device temporarily and return later. So if the software requests a configuration write or any other type of read, the root complex may automatically retry the request. Then the header type. So let us understand the configuration address port. So So before this, let us understand there are actually two ways to access the configuration space. So do you remember what we discussed about configuration space in our last lecture? So let us do a quick revision. So PCIe expands the configuration space for each function. So every PCIe has a 4 KB of configuration space. So this space is divided into several sections. The PCI compatible space. So this is originally 256 byte configuration area that older PCI software can access. So it is where important things like PCI Express capability are stored. The and then next we have the extended configuration space. So this is where more advanced features like error reporting, budgeting, or virtual channels are stored. So this space is only accessed by modern PCI systems using an using so this space is only accessible by modern PCI system using an enhanced method. So think of the 256 bytes as basic settings area. And so why only the root complex can make the configuration request? So in PCI system, the root complex which is connected to the processor is only part of the system allowed to make configuration request. So, in other words, root complex acts like the manager of all configuration activities. So, this manager sends the configuration request like instructions to the PCI devices and make sure everything is set up properly. So, why only the root complex is needed for this? Because allowing other devices to change the configuration could create a chaos. Imagine if every device could start changing things without permission, it would lead to conflicts. So only the root complex has special permissions. And one more important thing is that the configuration transactions flow downstreams. So, since only the root complex can send configuration requests, the request can only flow downstream. This means the configuration request start at the processor through the root complex and travel to the devices below. So, uh, devices on the same level cannot send the configuration request to each other. So these configuration requests are routed based on uh, BDF, which we learned yesterday, bus number, device number, and function number, which tells the system exactly where the device is located in the PCI topology. So let us now understand uh, how configuration transactions are generated. So most processors, so there are two ways to access the configuration space. First is the legacy PCI mechanism. So this uses an in- I this uses an IO indirect access method. So this is a method where the system access the device configuration registers directly. So the problem with older system was that there was not enough IO address space. It was only 64 KB available for IO. So by the time PCI came, the space was cluttered with many devices. To solve this, PCI used a technique called indirect addressing mapping. So this means that instead of assigning each device a separate IO address, the system uses one register for target address and other register for the data being sent to read from the address. Next, the enhanced configuration mechanism. So this method uses memory mapped access, which is more common in modern systems. So it allow configuration space to be accessed through the device memory address. So let us now understand the configuration address port. So the configuration address port is an important mechanism used by the processor to access the configuration space of PCI devices. So when a processor needs to interact with PCI configuration space, it writes to the configuration address port to specify which PCI device and register to target. So the address is written in a structured 32-bit format, as you can see here. So let us understand it by doing a breakdown of this 32-bit address. So bit 0 to 1 is hardwire and read only. So they always return 0 when we read it. So this, and then we have uh, 2 to 7, which are the register number. So this specify the target keyword or register number in the configuration space of the device. So this defines which dword in the PCI's device's configuration space you want to access. So there are 64 dwords in first section of configuration space, meaning the field can address any of these first 64 locations. Then we have 10, 8 to 10. We have the function number. So it identifies the function within the PCI device. And then 11 to 15 we have the device numbers, and 16 to 23 helps us identify the bus in the PCI hierarchy. And the next 30 to 24 is these bits are reserved. So, and next we have bit 31. So, this controls whether or not the processor's access to the configuration space is enabled. So it can, so this can be bit 31 can, when the bit 31 is 1, it is enabled. So the configuration space mapping, meaning the processor can access the configuration space of the PCI device. So when bit 31 is 0, then the access is treated as a normal IO request and no configuration access occurs. So let us now understand the host bridge and the bus number. So the host bridge in the root complex, as you can see here, so the host bridge in the root complex is responsible for connecting CPU to different PCI buses and devices. So it contains two important registers. First is the secondary bus number. So this represents the number of bus directly connected to the host bridge. And the subordinate bus number. So this defines the maximum bus number that can be accessed downstream from the host bridge. So these two registers help the host bridge determine which bus device you want to uh, communicate with the with is located on. So, so when a configuration request is made, the host bridge check if bus number in the request matches the range of buses it can access, which is determined by secondary and subordinate bus number. So if the target bus is equal to secondary bus number, the host bridge recognize that request for a device directly connected to the bus. So, and it sends a type 0 configuration request, which is a request to configure a device directly on the bus. And if a target bus fails between the secondary bus number and subordinate bus number, the host bridge forwards the request as type 1 configuration request. This means the request is being passed to another bus downstream, where the budge where the where another bridge will handle it and possibly forward it further. So let us now understand what is the type 0 configuration request and type 1 configuration request. So a type 0 configuration request is used when when the target bus number matches the secondary bus number of the bridge. So this indicates that the target device is located directly on the bus connected to the secondary side of the bridge. So in the last lecture, we learned how to determine the secondary bus number and the subordinate bus number. So let us once again revise that concept. So here is our bus 0. As you all remember, we always number bus according to the depth first search method. So first we will number this one. This is bus 0, bus 1, bus 2, bus 3. And this is bus 4. And this is bus 5. Bus 6 is here. Bus 7, bus 8, bus 9. So how we will now number the secondary and subordinate. So secondary, as we can see here, this is a device 0. just below it we have the bus number 1, and so the secondary bus number for this is 1, and the subordinate, which is the uh maximum bus number below this device, which is 4. So subordinate will be assigned as 4. And we can also see here that, and the primary bus number is the bus on which this device is. And here, just below this device, we have bus 3. And this is the maximum bus number below this. So secondary and subordinate is same. Like for example, here also for this device 0 on bus 5, on the bus 6 we can say what will be the secondary bus number for this. It is 6, because the bus just below is 6 and the maximum bus number is 9. And how we assign the BDF number to the devices? So like for example, if we want to determine the BDF for this here, so this is device 0 and its bus number is so based on the function, if the function number is 1, actually if we think it is not given here, so bus number is 1, device is 0, and if the function number was 0, so we would have assigned the BDF for this as 1 is to 0 is to 0. So if you want to learn about how to assign the PDF, you can refer the last lecture. So let us now move on to what is type 1 configuration request and type 0 configuration request. So a type 0 configuration request is used when the target bus number matches the secondary bus number. So I just now told how to find out the secondary bus number. So when the target bus number matches the secondary bus number of the bridge, so this indicates that the target device is located directly on the bus connected to the secondary side of the bridge. So what are the steps involved in this? So devices on the secondary bus check the device number field to determine which device is being targeted. In PCIe, endpoints on an external link are always assigned as device 0. Then next to the selected Next is the checking the function number. So the device selected then checks the function number to identify which function within the device is being accessed. So devices can have multiple function. For example, a network card could have a control function and a transfer function. Next, selecting the register. So the selected function uses a register number field in the request to determine which dword or the 32-bit block in the configuration space is being accessed. So the first dword byte enabled field specify which bytes within the selected dword are to be read or written. So what is the format of type 0 configuration request header format? So the type field is 00. As you can see here is the type field. So type field is 00100, indicating a type 0 request. So the format field specify whether the request is a read or a write. Now let us understand the type 1 configuration request. So a type 1 configuration request is used when the target bus number does not match the secondary bus number of the bridge, but the target bus number is written within the range specified by the bridge secondary bus number and the subordinate bus number. So in this case, the packet is forwarded to the bridge secondary bus as type 1 request. So what are the steps involved in this? So bridge handles the type 1 request, that is the endpoints on the bus ignore type 1 requests because these requests are meant for devices on the downstream bus. And when the request reaches the bridge compares the target bus number with its secondary and subordinate bus number. So if the target bus fails within this range, the bridge forwards the request to the secondary bus as a type 1 request. And next, if the target bus matches the bridge secondary bus, so the request is converted from type 1 to type 0 and is forwarded to the secondary bus for devices on that bus to process. So if target bus does not match the bridge secondary bus, it it is within the range, so the request is passed further downstream as type 1 request. So type 1 configuration request header format is 00101 indicating a type 1 request. So what is the difference between type 0 versus type 1 request handling? So when type 0 is there, it is used when the device is on the local bus, that is the secondary bus of the bridge. So devices on the bus directly process the request by checking the device function and the register fields. And what is type 1? So it is used when the device is on a bus further downstream. So bridges process these requests and forward them to the appropriate bus until they reach the target bus. So how legacy PCI configuration works? Let us understand this. So in the legacy PCI mechanism, the PCI configuration registers are accessed indirectly through the configuration address port and configuration data port. So here's how it works. The processor targets the device address, which is the bus, device, and function number to the configuration address port at a specific IO address, which is C0CF8H. Then the processor write or read the data from the configuration data port, which is 0CFC to 0CFFH. So the root complex check if the target bus is within the range, and if so, it initiates a configuration read or write request. So what is the problem with such mechanism? So let us understand this. So in older systems, accessing configuration space has two-step process. So the first, the CPU would have to write to the configuration address port. Next, the CPU would then perform a corresponding access to the configuration data port. So this was fine when there was only one CPU running a single thread. But in the modern system with multiple cores and threads, different threads might try to access configuration space simultaneously, so which could cause conflicts. For example, a thread A might want to write to the configuration address port, but before it can complete operation, thread B could overwrite the address within a few with a new one. So what is the new approach, which is the memory mapped configuration space? So to solve this, the spec writers found a new approach. So instead of using the old two-step IO port model, they mapped the entire configuration space into a block of memory address. So now accessing configuration space is done with one memory request, which directly generates a configuration request on PCI Express. So what is the trade-off for this approach? So this new method consumes more address space. So each PCI function now gets a 4 KB block of configuration space. So mapping a configuration space for all PCI functions require 256 MB of space address. However, this is a minor issue because CPU supports large memory address spaces, that is 36 to 48 bits of physical address space. So in such large spaces, 256 MB is insignificant. And so the issue being address is how to access and configure the PCR device efficiently given the limitations of legacy methods. So which use the restricted portion of address space for configuration. So to solve this, the writer of the PCI Express specification decided to map the entire PCI configuration space directly into memory address. So this allows a simpler and faster way of accessing configuration space with a single memory access command. So memory mapping of configuration space. So instead of using limited IO ports to access configuration registers, all PCI configuration space is mapped into a dedicated 256 memory address space. So each PCI function gets its own 4 KB of this address space. So mapping the entire space into memory allows the system to send a single memory request, which generates a configuration request on the PCI bus. So now understand the trade-off between the memory size and the address space. So the trade-off for this new approach is that it consumes 256 MB of memory address space. However, this is insignificant in modern systems. Thus, the new method allows for much more straightforward configuration access without worrying about the running out of the IO space, but at the cost of using some of the available memory address range. So let us now understand how multi-host system works. So in systems with multi-root complexes, there is a challenge. So when it comes to accessing the configuration space, so the configuration address and data ports can be duplicated across the different root complexes, but there must be a system to prevent conflicts. First, let us about learn about the first conflict. That is, first problem with this system is that preventing the contention. So what do you mean by contention? So it means conflicts. So when the multiple root complexes are present, they share the same IO address for configuration. So however, to avoid contention between them, only one root complex bridge is active at a time during configuration. So how it works? So when the processor writes to the when the processor writes to the configuration address port, the port that, or we can say the port that specifies which PCI device and function is being accessed, so only one of the root complex will respond and participate to the transaction. And next, the enumeration process. So during enumeration, the software discover all the buses and devices under the active root complex and assign them the bus numbers. So after the first root complex finishes, the second root complex is enabled. So the software assigns it a bus number range that does not overlap with the first root complex numbers. So by ensuring two root complexes, we have non-overlapping bus numbers. So both can operate without conflict, even though even though they see the same configuration requests. So now configuration port access. So once this step is done, any access to the configuration address port is seen by both root complexes, but only the one responsible for the target bus will process the request. So the selected root complex act as a gateway uh, to the appropriate PCI bus. So if the request for a device on the secondary bus, if it converts to the request to type 0 configuration access. If the request is for bus further down PCI hierarchy, it converts it to type 1 configuration access. So let us get started with one last topic, that is the header type register structure. So earlier we discussed to determine whether a PCI function is an endpoint or a bridge, we use information from header type register. So which is the offset 0EH in the PCI configuration space header. So here is how it works. So the lower 7 bits of the header type register identifies the function type. Here 0 indicates it is the endpoint, 1 indicates the PCI to PCI bridge, and 2 is for legacy device which is not used much today. Then next, the bit 7 of the header type registers. This bit indicates whether the device is single function or multiple function. 0 is for single function device and 1 is for multifunction device. So what are the steps to determine if a function is a bridge or endpoint? So first we check the header type. So if the header type register value is 0, it indicates a endpoint function. If the header point register value is 1, it indicates a PCI to PCI bridge. So how do we check multifunctionality? So if bit 7 of the header type is 0, it is a single function device. So if the bit 7 is multifunction device, meaning multiple independent function could be implemented within the device.